Yes, the basic content of the chapter of waves is actually quite small, but it can be very confusing. Let me warn you firsthand. Confusing in the sense that, uh, for example, it might sound weird. The example, let's say the letter English letter P and the Italic letter rho, they pretty much appear same, but there is a bit of a sharp difference between them. So if you know the difference, you can distinguish them. So wave chapter needs that level of attention. You have to exclusively understand the difference between certain scenarios, and that way you would be able to apply your knowledge appropriately. The actual content is quite small, but it is quite sensitive for where you need to apply it and how you need to apply it. So you can solve it pretty easily if you understand the whole process pretty well. There are some basic graph drawings, there are some uh, very simple calculation. The formulas are also very simple, but it really requires good amount of understanding, because you need to choose properly what to apply where and what kind of problems actually mean what. I'll be emphasizing these things individually whenever these topics will show up in places. You will also have the class notes as well. Uh, but I just demand that you pay close attention to what I'm saying and don't uh, mess up stuffs. That's the important bit. So from our O levels, we have some definitions over here. I'd like you to, all of you, to read through these definitions. I am not planning to read these up. There are 6-7 definitions over here. A definition গুলো একটু পড়ে দেখো. If you have any question, you ask me about it. Everyone. Any question? Anyone?
No.
No. আচ্ছা, এখানে একটা জিনিস একটু অ্যাডিশনালি আলাপ করি, সেটা হচ্ছে ওয়েভলেন্থের বেসিক যে ডেফিনিশন আমরা ও লেভেলসে শিখেছিলাম, সেটা ছিল হচ্ছে দ্য ডিস্টেন্স বিটুইন টু ক্রেস্টস অর ডিস্টেন্স বিটুইন টু ট্রাফস or the distance between two compressions or two rarefactions was defined as wavelength, which is actually pretty correct in its content. But there are there are two things which is changing over here. One of the thing is that you have to mention the word successive. The word successive is pretty important. We can have a wave. Let's say this is a wave. Let's say we have a larger sort of wave. আচ্ছা হ্যাঁ, মনে করো, consider this solid line. So if you consider this solid line, এখানে তো দুই সেট ওয়েভ নেই। আচ্ছা, আমি একটা ওয়েভ আঁকি। Okay, roundabout. I think it will work. So let's say a wave that looks like this. And what is important that we have to mention the word successive, because by definition this much space is what we define as wavelength, not this much. If we only mention that the distance between two crests is wavelength, then it could equivocally mean this much is wavelength, this much is also important wavelength, but that's not the case. This much is twice wavelength and this much is only wavelength. So the word successive is quite important. That's the first thing. The second thing that I would like you to take note about is that they have used a new term, that what is meant by there are two successive particles that are in phase. Phase was a physical property which was part of the definition of your Oliver's chapter, Oliver's waves discussion, but it was never highlighted enough, because the concept of phase, or the content of the idea of phase, is a bit uh, what can I say? It's it's a bit detailed. Uh, the phase, essentially the phase of it, I mean, how do you define phase? Let me show it to you. The actual definition of phase is not included in your syllabus. I don't know why. uh, Let me just show you. Okay, yeah, this is a good definition. Have a look. Phase of an oscillating particle at any instant is a physical quantity which completely expresses the position and the direction of motion of particle at that instant with respect to its mean position. So phase of an oscillating particle is comprised of two different quantities, but it is a variable, or it is a quantity that is highly dependent on the time instant. So same particle, same oscillating particle can have different phases at different instants of time. Phase of a particle exclusively means that where that particle is located, the position, this term, where that particle is located at a certain instant of time with respect to its mean position or rest position or undisturbed position or equilibrium position. They can be said to by a lot of different names. And also what is the exact direction of motion of that particle at that instant. These two properties together make up the term phase. So what this means is that two particles can be in the same position, but if the directions are opposite at any given time, they would not be in the same phase. If two particles are at same position, it means same displacement away from the equilibrium position. I'm using the term displacement because a particle can be, let's say, 2 centimeter above equilibrium position and 2 centimeter below equilibrium position. These two positions would not mean the same thing, because above can be considered as positive displacement, like typical ways that we do, and below can be considered as negative displacement. So you have to consider the direction or of the displacement as well, or the position of the particle with respect to the term, whether it is above the mean position or below the mean position. That's a pretty important thing to consider as well. So considering that, we by position would mean that displacement of the particle at that instant at any point of time, and also the direction of motion. Direction of motion means it is possible for an oscillating particle to be going upwards or downwards at a specific displacement, because if we try to observe the actual motion of a single oscillating particle, let me put it, let's say this is the equilibrium line. A particle is having its motion along this vertical line, so let's say equal space up and down, because I'm considering the amplitude to be equal. Okay, so what is very much possible that this particle is still gonna go up and down and cover this entire space for its oscillation properties. So it's gonna go up and down. So if you consider any random position, let's say if we consider this random position, at this position, at some instance of time, it would be going upwards, reaching towards the crest position. At some other instance, it would be going downwards, leaving from the crest position. So direction of a particle at a specific displacement can also be different. It can be upwards, it can be downwards. So these two factors combinedly represents the phase of a particle. Multiple particles of a single waveform means the total amount of medium which is affected by a wave. Do you guys remember the definition of wave? Is the definition of wave given in this thing? Definition of wave is not given. Okay, let me show the definition of wave so that it would be easier for us to go forward. কারো কোনো কোশ্চেন থাকলে আমাকে বলো বা চ্যাট উইন্ডোতে লিখো, I'll respond to it. দেখো, in physics, mathematics, and related fields, a wave is a propagating dynamic disturbance. Disturbance would mean change from equilibrium of one or more quantities, sometimes as described by a wave equation. In physical waves, at least two field quantities in the wave medium are involved. At least two field quantities means, in this case, for example, for a mechanical wave that we talk about that involves physical particles, uh, which requires a medium to move by. For waves can be of two types. One is mechanical wave, and another is electromagnetic waves. Electromagnetic waves do not require a medium for propagation, whereas mechanical waves do require a medium for propagation. For example, most common example, the sound waves are mechanical waves. They require a physical medium, solid, liquid, or gas. But electromagnetic waves do not require any medium. They can travel without the presence of medium. But if there is a medium present in their pathway, they can be slightly affected by that medium, but they don't essentially require a medium to be passed from point A to point B. That's not essential. So the two field quantities that changes whenever a physical particle is moving, one of them is displacement, the other one is velocity. So these are the two variables that undergo changes for physical particles, which we'll be dealing with for most of our discussion in the AS chapter. So the point that I was trying to go, it goes further down this point. I mean, a lot of discussions are here. You can read this at your own time, in your own time if you are interested. I was interested about coming to this point. Wave is defined as a disturbance that passes through a medium from one point to another point. Disturbance means a change or from equilibrium position or the natural position of the medium of the situation. If you consider for how do you apply this for an electromagnetic waves, well, the way electromagnetic waves travel from one place to another place is by oscillating electric and magnetic fields. Oscillating electric field and magnetic fields essentially doesn't mean any involvement of any physical object. It means the value of electric field strength and the value of magnetic field strength. These are two defined quantities which can be measured by appropriate instruments. So the value of electric field strength and the value of magnetic field strength, these two variables undergo certain amount of changes as long as the electromagnetic waves travels through that physical location, or let's say empty space. So these are the two variables. Change of these two variables cause electromagnetic waves to propagate from one point to another point. So that's also another important variable that we would like to take into consideration. In physical waves, at least two field quantities in the wave are involved. Waves can be periodic, in which case those quantities oscillate repeatedly about. Sorry. So that is the important part. The wavelength in this case is defined for a progressive wave. It is the distance between any two successive wave particles that are in phase. That is the distance between two consecutive crests or troughs and blah blah blah. আরেকটা পয়েন্ট যেটা আমরা অনেক সময় কনফিউজ করি সেটা হচ্ছে wavefront. Wavefront means a line or surface joining points which are at the same state of oscillation, that is in phase. Example, a line joining crest to crest, a line joining crest to crest in a wave. So what does this mean? Wavefront is basically a hypothetical representation for a wave to exist in a medium. For example, if I give a very simple example, let's say water waves are happening on a water surface. Now try to think about it. Let's say we have a ripple tank or an aquarium and we are making some water wave happening. So if you consider that this is a side view of the aquarium or ripple tank, let's say the waves are happening like this. So waves are happening like this. This is the Waves actually are continuously moving. So if I draw the waves in this format, this would essentially mean that we are taking a snapshot of the side view of the wave propagation, or time was somewhat frozen, so that all the particles are currently viewed at their own position for the duration of time. But actually, if we allow the time to pass through, that the particles will essentially undergo movement. So all the particles in this, because this is a transverse wave, the direction of energy flow is from left to right, and the particle oscillations are perpendicular to each other, which means all the particles are moving up and down. Now, if you observe this exact thing, the ripple tank, this is a side view from the top. Let's say this rectangle, I'm going to draw up a rectangle over here. So let's say if I draw the top view of this ripple tank, let's say this is the top view of the ripple tank. And let's say uh, the waves were made by a rectangular dipper. Let's say this is the rectangular dipper. There is, I'm gonna fill that up with some color. Let's say brown, maybe wooden dipper or something. Let's say we have a dipper over here. This is making the waves going left and right. Now you have to understand, all the particles that are present in this water medium, they are all going up and down. So in this case, they are actually getting closer to us and they're getting farther away from us. So from our viewpoint, the motion of the particles are perfectly vertical. For that kind of a motion, how could you possibly represent the presence of wave in this case? That's actually pretty difficult, because from the side view it is possible for us to draw the curved shape of the surface, but how do you represent the curved shape over here? That's basically where the idea of wavefront comes in. Wavefront is basically uh, an imaginary line which we can get by joining all the same phase particles which are located side by side. So for example, let's say if we draw multiple lines joining all the crests. So let's say if I draw a solid line over here and consider this as a wavefront, this would mean that all the particles, water particles which are present at this line, they are all crests and they're all side by side. So I can draw another one. Okay, this should be here. So let's say another one is placed over here, and then another one is placed over here, and then I can place up more. This would mean that all the all of these vertical lines, they don't actually exist in the water medium. You can never physically find out these solid lines. But the presence of the solid lines essentially represent that all the particles which are located, all the water medium particles which are located on this line, they are all at crest. Now, essentially a wave cannot be produced only by crests. There have to be crests and troughs. There has to be high points and there also have to be high points. This essentially always mean that between two crest position, there will always exist a trough position at the middle. In some cases, for the sake of easier drawing or less drawing, less complicacy in the figure. Sometimes the crests are, sometimes the troughs are not represented in the figure, but that doesn't mean they are not present. They're always present. So even if the troughs are not shown in the figure, they are definitely there. Sometimes also they can be the troughs can also be represented by dotted lines. For example, I can draw up a line over here which might as well look like this and represent it by some dotted lines. So in this case, the solid lines could represent the crest positions and the dotted lines could represent the trough position. That is also one way of representing the waves. But in many cases, the troughs might as well be altogether not shown for the sake of easier drawing. So these type of lines are represented by wavefronts. Wavefronts is a pretty interesting idea for us because it is the whenever we talk about the speed of a wave, we essentially mean the speed of the wavefront. What I'm trying to say is that, let's say here is a certain wave. Try to understand. Here is a certain wave. Actually, let me just. Should I show you this with a circular motion? This is nice. Ah, this is exactly what I was looking for. This is undergoing some amount of damping, but can we stop the damping? Okay. বলবান এর কি দেখা যাচ্ছে সবার?
জি স্যার।
আচ্ছা, this is a physical way of representing a wave motion. So this is basically a simulation, but this can pretty well represent that how wave motion actually does its stuffs. One of the key aspect of a wave motion is that wave transfers energy and information from one point to another point. So it contains energy and information. How does energy does get transferred? Have a look. Whenever the wave is not happening, let's say, uh, have a look. Whenever the wave is not present, whenever the wave is not present in the medium, the intermolecular spacing between this particle is, I'd say, equal to their diameter. If you wonder what the particles are touching each other, how is the intermolecular spacing equal to the diameter? Well, considering the particles as particles, particle would mean they are not sphere. Particles would mean that they have zero dimension. So I can consider all of their masses located at their center. So if you consider from the distance between the center of one particle to the center of another particle, that would be equal to their diameter. So this is the amount of space that they have. Whenever we'll start to oscillate this thing, let's say if I give it a pulse, uh, have a look, the space between them changes. Okay, let me just oscillate it, and not slow motion. Okay, slow motion is good. Acha, let me pause this. So what you should see that, do you see that here the intermolecular space is increasing? There is significantly large intermolecular spacing, and over here the space is pretty low, and over here the space is pretty large. Do you see that? Whenever we are talking about a string, whenever we have a extended string, this is actually what happens. And whenever we, in a taut string, if we start to do oscillation, the string actually undergoes localized extensions. And whenever it undergoes extension, energy gets stored within this part. And if we keep on the oscillation, these shapes are gonna keep going uh, from left to right. So that amount of energy which got stored in certain segment of the, for example, if you observe that, if you keep looking, you'll see that this increase in intermolecular spacing will always exist from within this part. If I just go forward, you see as this shape is going to the right, I mean, this position of the wave is slowly going to the right, this increase in intermolecular spacing is also traveling. So what I'm trying to mean is that this part is always responsible to have some intermolecular. Okay. ড্যাম্পিং না থাকলে ভালো হতো। আচ্ছা, এই তো পারা গেছে ড্যাম্পিং ছাড়াই। আমি এই ড্যাম্পিং এর বারটা এতক্ষণ চোখে দেখতেছিলাম না, এইমাত্র চোখে পড়ছে। ওকে। ড্যাম্পিং না দেওয়াতে যেটা হচ্ছে, the wave is maintaining its energy content throughout, so it is undergoing equal amount of vibration all together. আচ্ছা, this is sort of like a stationary wave. However, we don't want a stationary wave, so let's say we reduce the frequency, restart. আচ্ছা, এটা একটু মোটামুটি দেখতে পদের। এখন ফ্রিকোয়েন্সি বাড়াই দিলে মনে হয় আমরা টিপিক্যালি যে ওয়েভ চাই সেরকম ওয়েভ, হ্যাঁ এরকম একটা ওয়েভ পাওয়া গেল। আচ্ছা, so the reason I actually came up over here to show you one thing, সেটা হচ্ছে whenever we talk about the speed of a wave, what we essentially do mean is that at what speed the crests or the troughs are traveling. So if you consider this is the crest of a particle, this is the crest of a wave. So let's say here starts the crest and it slowly goes forward. So at what speed this crest is moving through the medium is basically what it means by the speed of the wave. So one easy way to obtain the formula v equals to f lambda, you know this formula v equals to f lambda, the defining equation for wave speed, frequency, and wavelength, is to have a keen observation for what is actually happening. What I need you to see, try to understand. Let me pause this over here at the crest position. Okay, this will be the crest position. When this dot is at the top, this is the crest position. Now I want everyone to observe, as in the amount of time this thing will make a complete full circle is what we're going to define as time period. What is going to happen in this time period, as this black dot of this circular rotator is going to travel all the way to the bottom position, this green dot is going to travel all the way to its bottom position or the lowest position. And then as this black dot is going to travel upwards, this is going to go upwards as well. So if I go for a bit of slow motion, have a look. Do you see that? This is happening. So let's try to consider that whenever in that amount of time period time, this crest is gonna show up exactly over here. This is the total wavelength. Have a look. From here to here, this is one wavelength. In one complete oscillation of time, this crest, I mean, I'm not talking about this particle, I'm talking about the shape of the wave. This crest is gonna come up over here. Have a look. This crest is traveling, and it just showed up over here. So in one time period amount of time, the amount of distance that any crest or trough or any wave, to be more exact, covers, that is exactly 1 lambda. So what that essentially means is that in t time, the distance covered is lambda. So in unit time, the distance covered would be lambda by t. And the distance covered in unit amount of time is essentially what is defined as speed. This is the basic formula for speed and time period. And also from the definition of frequency, we know that f equals to 1 by t, because t time is required for one oscillation. So in unit time, it gives 1 by t oscillation, which is frequency. So if we replace 1 by t over here, we can get f lambda equals to v. That's the defining equation for a wave. The point that I'm trying to establish over here is that you understand the concept that what do we mean by the wavefront. Wavefront and crest and trough position pretty much mean the same thing. Wavefront is basically the line joining through a lot of crests or through a lot of troughs, whereas simple crest or simple trough is a simple thing or a single thing. It's not produced by a lot of different things. Oh wow, wow, this is a good simulation. আচ্ছা, এই সিমুলেশন এখন হাতা পিতা করে লাভ নাই। এগুলো আসবে ড্যাম্পিং। আচ্ছা, ড্যাম্পিং তোমাদের আসবে না, ড্যাম্পিং আসবে হচ্ছে A2 তে। আচ্ছা, এনি কোশ্চেন সো ফার, এনিওয়ান? এই পর্যন্ত বুঝা গেছে যে এই ডেরিভেশনটা কিভাবে হইলো, এটা কিভাবে আসলো? এভরিওয়ান?
Yes, sir.
Yes, sir.
আচ্ছা, if you have question, you can ask me or you can put it in the chat window, no problem. I have the chat window open over here. So these are the basic idea. So এখান থেকে আমাদের সেই ডেফিনেশনটা আসছে, এটা গেল। এরপর হচ্ছে আমাদের কিছু ম্যাথ আছে এখানে, বেসিক ম্যাথ, এটা সিম্পল জিনিস। রিকল এন্ড ইউজ দ্য রিলেশনশিপ ইন্টেন্সিটি প্রপোর্শনাল টু অ্যাম্পলিটিউড স্কয়ার, এটা আমাদের লাগবে। ইন্টেন্সিটির বেসিক কনসেপ্টটা তোমাদেরকে বোঝাচ্ছে, এখানে বলে দেওয়া আছে। ইন্টেন্সিটি ইজ ডিফাইন্ড অ্যাজ দ্য রেট অফ পাওয়ার ফ্লো, রেট অফ এনার্জি ফ্লো per unit time, which is power, per unit cross-sectional area, perpendicular to the direction of the wave propagation. Definition তো অনেকগুলো different টার্ম আছে, বুঝো। It means power over area. এই কোশ্চেনটা খেয়াল করো, intensity equals to power over area. So how much joule per second is traveling through 1 meter square area in the path of the wave? In the path of the wave, আমি বলতেছি এই সেন্সে বোঝানোর জন্য যে that is perpendicular to the direction of the wave. For example, if we do consider for ripple tank wave like this, uh, if we do have a surface over here that has a specific size of exactly 1 meter square, how much energy is passing through that wave for 1 meter square area of that wave is what we can talk about, what we can consider as the intensity of the wave. Well, what is important that the alignment of this considered surface should be perpendicular, because if it is not perpendicular, you're going to have different values. What I mean, আচ্ছা, এটা অ্যাকচুয়ালি রিপল ট্যাঙ্কের জন্য দেখানো একটু ডিফিকাল্ট। আমি এটাকে লাইট বাল্বের জন্য দেখাই। মনে করো হচ্ছে এখানে আমাদেরকে একটা লাইট বাল্ব আছে, লেটস সে দিস ইজ এ লাইট বাল্ব, লেটস সে দিস ইজ এ লাইট বাল্ব। এখন এই লাইট বাল্ব থেকে এসেনশিয়ালি সব ডিরেকশনে আমাদের এনার্জি ডিস্ট্রিবিউট হচ্ছে, আস্তে আস্তে ছড়া যাচ্ছে। সো ইফ আই ব্রিং আপ if I want to calculate the intensity of this source at a distance, let's say from the center, মনে করো from the center থেকে মনে করো হচ্ছে let's say 25 সেন্টিমিটার, 25 সেন্টিমিটার দূরে আমি এই সোর্সের ইন্টেন্সিটি কত সেটা আমি এখানে মেজার করতে যাচ্ছি। So I have to calculate somehow the amount of power that goes to unit meter square from this space. Now একটা জিনিস ইম্পর্টেন্ট, সেটা হচ্ছে এখান থেকে আমাদের এনার্জি গুলা কিন্তু radially বের হচ্ছে, which means they are not all in straight lines, so they are coming out radially, so there is a bit of a curved surface if you have to consider this. So one of the ways we can overcome this problem, if we use an intensity meter or the physical device that would allow us to measure the intensity, that is actually quite small. মনে করো হচ্ছে আমরা একদম পিচি সাইজের, একদম অনেক পিচি, মনে করো হচ্ছে এইটুকু সাইজের একটা ইন্টেন্সিটি মিটার আমরা এখানে প্লেস করলাম। It's a very small surface, considering the idea that a very small flat surface of a very large sphere can be considered to be a effective tangent of that spherical surface. So we can place it up over here, measure it up how much is happening, and then we can divide the calculated power that is measured in this surface by this relevant surface to get how much power will be available for 1 meter square. So that is the idea of intensity. Intensity is basically a measure that how much power is available per square area, for a certain location. And it is essentially true that the further you travel from a source, your intensity will essentially go down, because the energy will be spreading out in a radial direction. So that's the idea of intensity. Intensity is dependent upon three factors. Those three factors are all have a squares on them. I think, is it given? এখানে শুধু অ্যামপ্লিটিউডটা দাও, বাকিগুলা কি এখানে আছে? আচ্ছা, পরে কোথাও থাকতে পারে। এনিওয়ে, আমি তোমাদেরকে এখন বলে দেই, since this actually showed up. Intensity of a wave is directly proportional to amplitude squared. Intensity of a certain wave is directly proportional to frequency squared. And also intensity of a wave is inversely proportional to the distance squared, which is sometimes written as r or sometimes written as d as well. I'm using the term r because in many cases we consider spherical objects, so r can be represented as the distance from the thing to the specific designated point where we're trying to measure the intensity. That is also possible. আচ্ছা, so these are the three dependency of intensity. আচ্ছা, frequency নামে একটা জিনিস বলি, সেটা হচ্ছে depending upon whether the wave requires a medium to propagate from one place to another place, we can say that wave can be of two types. We can have transverse waves, we can have electromagnetic waves, we can have mechanical waves. But one thing you should always understand, without the presence of physical material, or without using matter, we cannot make objects to emit wave. To create wave, we essentially require physical material. To create wave, we require physical material, and whenever physical material oscillates or vibrates, it produces a charge. It produces a wave, and the frequency of a wave is a defined factor depending on its source. Whenever a source produces a wave, the frequency of that wave is defined at that instant, because if the source is vibrating at high frequency, the wave is going to have a higher frequency, and vice versa. So frequency of a wave, no matter what, cannot be changed once it is already released from the source. The only thing that could possibly change the frequency of a source is exclusively the source. Sorry, the frequency of a wave is exclusively the source. The reason I'm highlighting this point so vividly is because to give you the idea that frequency of a wave is basically a unchangeable property of a certain wave. You cannot change the frequency property of a given wave. You simply cannot. By changing the medium, you can effectively change the v and lambda. Think about the formula: v equals to f lambda. So visualize it: v equals to f lambda. So if you consider the f as a constant, you can convert this into a proportionality where we can get v is proportional to lambda. So this would mean that if you have a certain medium in which the wave travels faster, obviously in that medium the wavelength is going to be bigger, because v is proportional to lambda, and vice versa as well. For in a slower medium, the wavelength would be smaller as well. So if you make a certain mechanical wave, or maybe an automatic wave, for example light, to travel from one medium to another medium, depending upon how fast that wave can travel through that medium, it can have different values of lambda, but its frequency f will always remain unchanged. Frequency will never be changed. This is one of the key reasons that it is usually the typical range, uh, the typical distribution of the electromagnetic spectrum, the gamma rays, X-ray, UV, visible light, infrared, microwave, and radio wave. That separation of electromagnetic wave region is more conveniently expressed in terms of frequency other than in terms of wavelength. Even if in some cases you find this that this electromagnetic spectrum is distinguished or separated in terms of their wavelength, the only reason they are considering all of those waves are traveling through empty space, where all of them have a fixed value of their speed, which is 10 to 10 to the power 8 meters per second. So এটা হচ্ছে একটা important bit. In vacuum, all of them have the same speed. So because that v is a constant, so frequency would be inversely proportional to thing, inversely proportional to lambda. So ওটা এখান থেকে আমরা individual lambda গুলোকে define করতে পারি, but that lambda is not a, what can I say, মানে exclusive unchanged property of those waves. Going through different medium in I mean, if visible light travels visual light, let's say if uh, X-rays travel through vacuum, they're going to have one range of lambdas. If they travel through a stone, they're going to have a different value of lambda. Depending upon medium, their lambdas can change, but their frequency will always remain unchanged. This is a very important term we have to understand. So whenever we see this thing, that I proportional to f squared, this means that if the source is vibrating at a higher frequency, or if a certain wave has a higher frequency, essentially its energy content would be higher. This is also why we say that gamma rays are really hazardous for us, because the amount of energy concentration that gamma rays actually carry out, they have a potential capability to make significant molecular separation or to dissociate molecular bonds. So if that happens in genetic material, that can give rise to certain sort of tumor growth or other problems. So that's why gamma rays are hazardous. X-rays are also hazardous in a way, but it's not that much. I mean, the how can I put this? I mean, if we have to take an X-ray, if we go ahead and take an X-ray for any part of our body, we expose our body to an increased rate of radiation. That increased rate of radiation always give us a certain higher probability to develop tumor or cancer cells within that body part. But our body can always handle with a certain amount of mutation. because we have natural background radioactivity around us, so our body can handle that. But too much exposure of radiation, if it goes beyond the capability for the body's immune system to deal with it, then there is a high possibility that people or animals can develop tumors or cancers. Anyway, that's not the important bit for this part. I wanted to highlight that frequency is a variable that is not medium dependent. Frequency is a variable that is exclusively source dependent. এই ইনফরমেশনটা ভালো মতন বুঝা গেছে কিনা সবার?
जी सर। Yes, sir.
আচ্ছা, এটা গেল।
Is amplitude affected by the medium?
Yes, amplitude is affected by the medium. Yes, amplitude is affected by the medium because uh, amplitude is basically how much the medium particles get moved by the propagation of the wave. If the medium, there can be a lot of different variables, physically measurable quantities that can affect the amplitude of a wave in a medium. But if I just put it in a simple term, let's say if the intermolecular attraction forces of the medium particles is more strong, then they would require to deform less, or they would have to deform less to store the same amount of elastic potential energy. So what I'm trying to mean is that in this animation, the particles were spaced out at certain locations to have the particles were spaced out in certain locations, which was storing energy in them. If their intermolecular attraction force is stronger, then they are going to be spaced out less, which means their amplitude can be also smaller. The answer is yes. From different medium, we can have different amplitude. Yes. বুঝছো?
Yes. Which?
কই ছিলাম যেন? এরপর আছে হচ্ছে গ্রাফিক্যাল রিপ্রেজেন্টেশন অফ ট্রান্সভার্স ওয়েভ এন্ড লংজিটিউডাল ওয়েভস। আচ্ছা, হ্যাঁ, অ্যানালাইজ এন্ড ইন্টারপ্রেট গ্রাফিক্যাল রিপ্রেজেন্টেশনস অফ ট্রান্সভার্স ওয়েভ এন্ড লংজিটিউডাল ওয়েভস। এখানে একটা জিনিস তোমাদেরকে দেখাই। ট্রান্সভার্স ওয়েভের জন্য আমরা টিপিক্যালি একটা ওয়েভের যে শেপটা আঁকি, সেই ওয়েভ শেপটা পারফেক্টলি ঠিক আছে। That shape actually works out because the particles actually undergo that amount of movement. For example, let's say if you consider this is a water wave, if this is the shape of the water surface at a certain instant, this would mean that this particle is at equilibrium, this particle is small portion towards the equilibrium, this particle is exactly at the positive maximum position plus a. And you can, by observing different position of the particle, you can find out the individual displacements. That's not a big deal. But in some cases, or in many cases, we also represent sound waves as sinusoidal curves. Now, sound waves are longitudinal waves, which means they don't essentially travel up and down if the wave is traveling from left to right. They are essentially moving left and right. So there are layers of sound atmospheric molecules which are undergoing compressions and rarefactions in different places. So how is it logically acceptable that we represent sound waves as sinusoidal waves? The answer is a bit simple. We use sinusoidal waves to represent a longitudinal wave exclusively for the ease of representation and drawing. Longitudinal waves never produce sinusoidal curve shape or up this type of crest and troughs. For example, this is what they are showing over here. What they are showing that this is the actual motion of a longitudinal wave, but this motion was represented in terms of amplitude with respect to the distance from the source, like this. Try to understand. This is not how the medium looks like. This is not the shape of the medium. This for a transverse wave, this was the shape of the medium. But for a longitudinal wave, this is not the shape of the medium. This thing reads displacement from the equilibrium position. So how far each individual particles are away from their individual equilibrium position is plotted over here with respect to distance from the source. Let's say this is the distance for this is the source, and at the source the particle is at equilibrium, so this is 0. This particle has a displacement of this much. এই যে এটা ছিল equilibrium position, এখান পার্টিকেলটা এখানে আছে, সো এইটুকু স্পেসকে আমরা এখানে with appropriate scale label করছি. Then this next particle had the maximum displacement, which we represent as the amplitude. Then this particle has a bit less, this particle has even less. So all of these particles, I mean, from here to here, all of these particles had their displacement from to the right side of the equilibrium. So we all showed them as positive displacements. At this point, all the this particle is at equilibrium. This is this particle. All of these particles, they had a displacement to the left. So have a look. This particle has moved a bit to the left. This particle has moved even less, more to the left, and this particle has moved the most to the left. And then reduction, and once again, this particle is located at the center. So this is the essential movement. This is the physical representation of how the particles are arranged. If we represent that measurement of their displacement with respect to the distance of those individual particles, equilibrium position from the source, then we get a graph like this. This is not the actual shape of the medium. The actual position or actual condition of the medium is like this. Particles are somewhere getting too much clumped together, which is represented as a compression. This is the center of the compression, and particles are sometimes at far apart from each other, which this is represented as the center of rarefaction. So this is the basic idea that why a sinusoidal wave can also be used to represent a longitudinal wave. It does not represent the actual shape of the medium. However, it is a plotting of two different quantities, one with respect to another one. এই ডিফারেন্সটা কি বুঝা গেছে বলবান যে কেন লংজিটিউডাল ওয়েভে আমরা সাইন কার্ভ ইউজ করি? এটা একটু ভালো করে খেয়াল করো সবাই। টেক সাম টাইম, টেক এ লুক এট দিস ফিগার। আই থিংক মাগরিবের টাইম হইছে না? I think so.
Yeah.
Achha. So we're going to take some break. This is 6:32, so we'll resume class at 6:40. I'm giving 8 minutes. So এটা থাকুক এখানে, তোমরা নামাজ পড়ে আসো, then we'll resume the class at 6:40.